Um, well, now we are ready to go to the following session, and now, yes, I'm the chair or chairwoman, as I like to say. The next session is about citizen science, which is a very important topic these days, and because it's a mix, it's an interface between professional activity and people doing a part, even a small part of a scientific work. At the beginning of the symposium, this session was completely devoted to the eclipses. So for this, you see citizen science and solar eclipses. And we maintain the denomination because you will hear some talks about eclipses. But, well, now the eclipse will be watching by streaming, as you know. Just a few selected person can be there. And these selected persons are mainly the local inhabitants. So it's a very interesting moment to see if the local people can do what the astronomers indicated during these last months, and can be not only the protagonist, but also the link between the event, this total solar eclipse, and the rest of the world, which is ready to see the phenomena. So now the first speaker is not at the room, so I will invite the next one. Yes, no, he is not here, so I will invite the next one, which is Alcides Ortega. I think Alcides has all the permissions. Let me see. Alcides Ortega, no, you are here. I will put you as co-host.
I'm here.
Are you there? Alcides is from the University of Carabobo, Valencia, Venezuela. Are you there? Can you enter? Can you open your camera? Hello, Alcides. How are you? How is your country?
Fine.
Fine, right? Yes, I know. Okay. Well, Alcides will talk about Astronomical Society of the University of Carabobo, scientific enculturation agent in the city of Valencia. Remember, in America, there are a lot of names similar than in Europe. Valencia, Venezuela, not Spain. Try to share your screen, please, Alcides.
Good.
Do you have any problem?
Share
the screen.
My English is very poor.
Don't worry. We are not English speakers at all, so
no.
We are in the same boat. Yes, on the same boat. There are a few English speakers here, and everybody are very friendly and
I think in the big data and technology age, I make a video using robotic translator. I wish pass play it.
I see this. I wrote you yesterday, right?
I believe that interesting video about it.
I have not your video. Can you share your screen, please? Would you like to wait and I can change the speakers if you want, and you have time to organize your talk, okay? Emmanuel, are you there? Emmanuel Rollinde?
Hello.
Hello, Emmanuel. Sorry, you asked me for some time to check, and I had it.
No, no problem.
Okay.
So I was hoping to have like 20 minutes more to get rest.
Emmanuel, you have yes, all the permission. So
you want me to, there is someone
perfect.
sharing.
We can see. Can you turn off your camera, and you can see your face?
Hello.
Oh, okay.
My name is Ortega from the Astronomical Society of the University of Carabobo, and I'm going to talk to you about the activities we carry out as a scientific enculturation agent in the city of Valencia, Venezuela. The Astronomical Society of the University of Carabobo is a permanent scientific dissemination activity which uses astronomy as a tool for the scientific enculturation of the population and for the non-formal teaching of sciences and technology in the city of Valencia, Venezuela. The Astronomical Society of the University of Carabobo began as a permanent activity for the study and dissemination of astronomy at the end of the last century, coinciding with two notable astronomical events in the region. Although there were already groups of astronomy fans in the region, they did not carry out permanent outreach programs. The transit through the perihelion of Comet Hill Bomb in April 1997 dazzled the local population, showing itself as the brightest comet of the century and remaining visible to the naked eye for a long time. It gave rise to several days of astronomical observation and continuous interaction with the community. The total solar eclipse February 1998, a phenomenon of singular majesty that led us to plan activities outside our geographic environment, moving to a location within the totality strip at a distance of more than 300 kilometers where we can appreciate the event. The logistics carried out allowed us to facilitate the transfer of the followers of the activity interested in observing and interacting with the host community to develop cultural exchange activities prior to the event. For 2 decades, this activity has brought together the university community, the Carabobo State Engineers Center, the Venezuelan Association for the Advancement of Sciences, and the associations of astronomy fans with the purpose of disseminating science and technology. The Astronomical Society of the University of Carabobo, following the premise formulated by UNESCO within the framework of the Education for a Sustainable Future project, launched in 1996, bases its learning activities on the cognitive theories of Gaston Bachiller and Edgar Morin, according to which the approach to the dissemination and popularization of astronomy should focus on knowledge for life and on overcoming epistemic obstacles between expert knowledge and knowledge taught. Bachiller, in his work, contributes his conception of epistemological obstacle, and he poses it as the psychological difficulties that do not allow the appropriation of knowledge, minimizing the transition from a pre-scientific state to a scientific state through the observation of phenomena. In the scientific spirit, Bakelard advocates the imitation of the rationalism and values of science rather than its method. Scientific culture must be in a state of permanent mobilization, replace closed and static knowledge with open and dynamic knowledge, dialectize all experimental variables, favoring the evolution of reason. The verbal obstacle prevents the advancement of science. Language plays a preponderant role in the recognition of phenomena and must be used in a responsible way of using explanation, associations, linguistic subjectivities, puts the act of understanding and the act of communication at risk. The approach to the natural world through phenomenology opens the way to the formation of scientific knowledge in a continuous search for knowledge. Scientific discursive rationalization is opposed to basic convictions such as light certainties. One should not start from the truth, The school knowledge learned is in permanent doubt and must be continuously validated. The obstacle of pragmatic knowledge utility constitutes a principle of exclusion and an epistemological obstacle to knowledge. The obstacle of quantitative knowledge, also known as false rigor, blocks thought. It is a primary symbolic system that sometimes prevents the understanding of new knowledge. Warren proposes restructuring education in the 21st century through what he called the 7 knowledge for the education of the future. It postulates that education should be for life in the here and now. In addition, it is necessary to reorganize not only the act of teaching, but also the fight against the defects of the system. Astronomy as a common scientific culture is important because it responds to Morin's principle of rational uncertainty, which invites us to ask ourselves about nature and the concept of humanity. It allows to inquire about the place of humanity in the universe and the finitude of life. This is where astronomy reveals itself to us as a science of interconnection between different disciplines and addresses fundamental problems. The regularities of the movement of the stars in the celestial vault showed that the natural world could be rationally understood, that there is an order and rules that govern it, and whose knowledge allowed our ancestors the development of agriculture and navigation. This cultural heritage on the role of astronomy to promote the study of nature. It is useful for non-formal collective education and for the dissemination of science and technology among young people. The activities of the Astronomical Society focus on the didactic transposition of knowledge, avoiding the details of the rigor of meta language. In the use of the scientific spirit in the sense of Bachelard's philosophy, and in astronomical observations of the present time, concordant with the idea of education for the here and
2 minutes, Alcides.
The philosophy of Edgar Morin.
Está a punto de terminar.
The Astronomy Society, in the process of enculturation, develops activities for the community in general, seminars, astronomy courses for amateurs, production of multimedia materials, videos, software, books, etc., and traveling exhibitions, all of them for non-formal education with a ludic style. Part of the activities of the Astronomical Society is to collaborate with the youth sciences festivals organized by the Venezuelan Association for the Advancement of Science, and also in the professional improvement activities of the Carabobo State Engineers Center. The Astronomical Society of the University of Carabobo is the one who produces the Astronomical Ephemeris of Venezuela for free, a work that was previously carried out by the Cajal Naval Observatory until 2006. The qualitative evaluation after 2 decades of activities of the Astronomical Society of the University of Carabobo allows us to conclude that astronomy can affect as a motivating axis for cultural appropriation and scientific enculturation by broad sectors of the local community, regardless of age, schooling, socioeconomic activity, or ideological cultural diversity. For more information, visit our website or contact us by mail. Thanks for your attention.
Okay. Thank you, Alcides. Now, can you... Sorry. Okay, don't worry. Now we invite Emmanuel Rollinde, I think.
Yes.
He's from France, so I think the last name is Rollinde.
Roland.
Rollinde, okay, very good. And He will share with us a presentation entitled Learning STEM with Astronomy, the case of F-HOU tools, SalsaJ and Human Orrery. Emmanuel?
Yes, thank you very much, Beatrice.
No, you're welcome.
First of
We
all,
can see very good. Yes, we can see very good your screen.
Okay.
If you turn on your camera, we can see your face also.
Yeah, my camera is on, no?
Let me see.
You don't see my camera?
Oh, well.
Okay.
Okay.
I start.
Yeah.
So I think the
Yes,
organizer.
perfect. Now it's perfect.
Okay. So thank you for giving me the opportunity to describe what we are doing with F-HOU. I changed a bit the title, but the content is the same. So I will first give a brief overview of the modeling astronomy. So our global philosophy in F-HOU is to train the teachers so that they can apply modeling astronomy in the classroom. And after that, I will give two examples. One where we do data analysis with the software SalsaJ, and then another one where we put students to do the model. That's what is called in action. So I go directly to modeling. So you might know this, this picture, which is a modeling cycle by Bloom and Lace. So the basic idea of modelization is to start with a real situation, to model first the situation, so to find the main parameters that are useful. And then you have this mathematization. It goes from the real model to a mathematical model. And then you have to resolve the mathematical model and come back to reality. Okay, so this is nowadays quite a standard modeling cycle. I like this other way to show it, which has been proposed by Tancredi, which is a French didactician. And it's basically the same, but in school, it's maybe easier to do. The point is to have an experimental field, which is the same as the real model here, and a theory and model space, which is basically the same as the mathematics here. And the goal of an activity, would it be in school or in science center or wherever, is to make the learner go from one space to another space and to work within each space. So I like this representation because it's less a cycle. You can work one way or the other. It depends on the activity you are doing. So that's why I talked about STEM, because by doing this and bringing in your mind the fact that you want to model, you have to do science activities, more physics, biology, chemistry, etc. And then you have to do mathematics. So you have to do technology, science, engineering, and mathematics. It's good to have this in mind as well in school or in science center. That's the connection with the STEM education. And then what is special about astronomy? I mean, because you could do these modeling activities in any topics, any subjects. But there are some points that I believe are specifics in astronomy. The first one is in astronomy, you have a single case situation. Okay. Sorry, you have a single case situation. So you cannot change the star that you are looking at. You cannot change the planet that you are looking at. You can see it only once. Okay. And then the second specificity is that you have only light to see the objects in astronomy. You cannot touch it. You cannot move it around. You cannot go around it. You have just the light to see it. And because of that, because it's a single case and because you have only light, then you need to model. And you need to do something like modelization. Sometimes when you work in topics where you can touch the object, you might believe that you could understand it without modeling. In astronomy, that's not possible. So it requires modeling. And also, astronomy does not have friction. And it's just in code because it's just, the point is that then you can explain the situations only with Newton's laws, with very simple Newton laws, without complex mathematics. And that's why Astro 101, which is a famous lecture in USA, is a favorite one for the students because there is less mathematics, but as much modelization. And at the end, when you go through those cycles, the students obtain the same results as the researchers do. And that's what we all want to promote in astronomy education, I guess. So I will show you two examples where we do this cycle with the students and where at the end they obtain the same result. So with simple mathematics and with a specific case that you cannot work out without modelization. So the first one is exoplanet detection. So we talk a lot about exoplanet, and it's something that is very fascinating and motivating, but it's more than that. If you want to find an exoplanet, you take images, you know that? You take many images during every minute or every 10 minutes, it depends. And when you look at that, you don't see anything. Where is the exoplanet? There is no way to see and to get in touch with the exoplanet. So you have to think about the model. You can also see the spectrum of the star. And again, when you look at the spectrum of the star, you can take spectrum at different time. Sorry, okay. And then you will see the spectrum moving, but you don't know why. There is no exoplanet here. So you have to go further and model the situation. You have to understand that if there is a planet, if there is one, it has to move around the star. The star has to move around the center of mass. You see, you have to do this model situation. It's not anymore the real situation, it's a model situation. And then you have to understand that because the source of light is moving, you will have a Doppler effect. And if you understand that, you can process to mathematization. You can process to a graph, for example, of luminosity, or you can process to a graph of Doppler velocity versus time. Because you do that, you can end up and find the exoplanet exactly the same way as the researchers find the exoplanet. So that's one example. The second example is a black hole. So this is a movie provided by Gonzalo et al., where you see the stars moving around the center of our galaxy. And again, that doesn't prove that there is a black hole, but if you follow the position of one star, one specific star, and you follow the position with time, you recover an ellipse. So that's simple geometrical mathematics. And this ellipse is explained by the Kepler law. And this proves that there is a mass at the center. This has been done in schools, in real classrooms. And they end up with the mass of the black hole. It is very similar to the mass that has been found by the researchers again. Okay, so those two examples are just an idea of what we promote in F-HOU, is to do astronomy, but not only to know about the astronomical objects, but also to apply a modelization, to see the strengthness of modeling a real situation and the interest of doing mathematics. Because at the end, you have what the researchers found. So I go to the next point, which is again a model. We like models, and but it's a model where your body is a model. So before I showed you, you can take real data and you make a model of the situation. But here, you don't take real data. You enact the objects that you want to model. So we do that with the solar system.
2 minutes.
Yeah.
Okay.
Yeah, we do that with the solar systems. So here you see the children moving around the sun at the center, and you have Venus, Mars, Earth, no, sorry, Mercury, Venus, Earth, and Mars. And you have Jupiter far away that is going very, very slowly. So with that, you can understand the velocities of the planets directly by your own body that enacts the model. So this has been made in many schools now, all over the world, and those are the ones that we have promoted with F-HOU. So you see here the children have drawn their own orrery. It's called an orrery. So it's also a mathematical activity. And then just to the last activity, that we use that now in the school to teach physics concepts And here, for example, is a concept of referential frame. You have here the students enacting the referential frames. And by doing that, they understand better the retrogradation of Mars. And it's just an idea that here we prove that they have clearly learned through this tool. Again, because they have done the modelization here with their body and before using the data. So it's not really a conclusion, it's more an opening that we are promoting now a new Francophone dynamic, and it's inspired by the creation of the Office of Astronomy for Education. So I invite you all to register, if you speak French, to this online Francophone conference that will be online, of course, from the 7th to the 9th of January. I just leave this, and if you can register or contact me for non-Francophone people. Okay, thank you very much.
Thank you, Emmanuel. Please put a link to the conference at the chat, because we will save the chat, and it's a good place to maintain this. Thank you for the talk.
I will do that.
We have the pleasure to invite the next speaker, who is Gonzalo Tancredi. Gonzalo, are you there?
Yeah.
Gonzalo. Oh, hello, Gonzalo. How are you? Gonzalo is, well, a colleague from Uruguay. He works at the Department of Astronomy at the University de la República, Uruguay. And today he will talk about one of his specialties, the Fireball Detection Network, BOCOSUR, a participatory research project. Gonzalo, thank you very much to be here. The stage is all yours.
Well, thank you for the invitation. Are you looking at you see my screen? Yeah, I think so.
Yes, it's very good, Gonzalo.
Okay. Well, thanks for being here. I would like to be in Argentina at this moment, but the situation is becoming very difficult in these times. I'm working at the University of la República, Universidad de la República in Uruguay, but I'm also the president of the Division F of the IAU, the Planetary System and Astrobiology. But this presentation is a collaboration with several postgraduate and undergraduate students, as well as other colleagues from high school observatories in the Consejo de Enseñanza Secundaria and the Observatory of Los Molinos that belongs to the Education and Culture Minister. Well, the name of our project is BOCOSUR. It's a citizen science project, and our mission is that university students, as well as teachers, researchers, together with members of the local educational communities, actively participate in the generation of scientific knowledge, collaborating in the operation and maintenance of a network of devices, proposing improvements to the prototypes and reducing the data. The scientific objectives of this work is to install a nationwide network for the detection of fireballs, bolides, bólidos in Spanish, bright meteors, estimate the frequency of the fireballs in the southern hemisphere, and identify new radiance. Well, this is a picture of a fireball that you might have already seen many of them, and in fact I have a very famous one on the back of my screen. Well, as I said before, the name of our project is BOCOSUR because it comes from Bólidos del Cono Sur. Well, first we start with developing our hardware. It's an all-sky camera that is based on a highly sensitive CCTV camera, a surveillance camera, and a fisheye lens. And we built a station, device that includes a mini PC, a temperature sensor, heating and cooling devices, GPS, Ethernet connection to internet. So this is the station. The total cost for this station is on the order of $1,500, and it's built by our own group. We buy the different items, and then we assemble all the things in our laboratories. At the moment, we have already installed 4 stations. One is on the rooftop of our Faculty of Science. Another one is in the High School Observatory in San Carlos Maldonado. Another one in the High School Observatory of Casupá, and the University Center in Rocha. This is the map of the stations that we have at this moment. This green one at the bottom, that are the 4. We are in the process of installing 2 more. The idea is that in the phase 1 of the project, we will have 6 stations separated around 100 kilometers, because assuming a field of view of 120 degrees and a firewall height of 80 kilometers, then we will have 3 stations that we could collect data from the fireballs. And most of the stations are being installed in the high school observatories in the interior of the country. In the phase 2 of the project, the goal is to have possibly on the order of 20 stations spread all over the country, and maybe even to neighbor countries like Argentina and Brazil. Well, the stations run an application developed by our group. The application, the name of the application is Bolidos, that control the hardware, start and end the videos acquisition system as a function of the sun height, and do the initial processing of the video. For example, we record only when we see something that, for example, moves in our video. The station works autonomously, reporting the events to the server. So we control the system through any desk. We use this remote control for the stations. Then the stations report the data to the server. We make internal copies in the server, and then we synchronize the data with Google Drive, and we give access to the data to different users. And these users analyze and classify the videos. So what we are working now is to create groups at different high observatories, high school observatories. The high school here in Uruguay is for ages between 15 and 17, and each high school observatory has a professor, has a teacher, and it's the leader of the group. And these groups, the idea is that they are downloading the video on their computers or cell phones, and even uses what we call the Ceibalitas. The Ceibalitas is a very successful project that has been developed in Uruguay for many years. It's a project internationally called one laptop per child. So they can use their Ceibalitas to analyze the videos. They classify the video in different groups: meteor, planes, animal, clouds, others. I will show you some example. And the classification will be used for identification of the fireballs and create a database for post-processing classification algorithm that we are developed based on machine learning. This is one example of a fireball, of a bolide. You can see it very clearly. But in addition to that, we have many spurious detection. For example, planes, birds, insects that are crossing, and they start our event detection algorithm, and then we record these videos. So we have to classify. Or we have, for example, some unknown things. For example, this bright thing that it's lighting here, or rain or clouds that could produce sun events. So the idea is that the students, the high school students, could help us in developing this classification scheme and contributing to the machine learning algorithm that we are developing. In addition, the idea is that further citizenship participation could be promoted. For example, the report of fireball sighting. For example, we have a Google form to report if you have seen a fireball, or we can also access to the International Meteor Organization fireball report. And this would be very useful it would help us on the evaluation of the completeness of the autonomous detection system and provide new data to improve the orbit determination. And in order to end with my dissertation, with my presentation, I have example that we are analyzing at this moment. This is a recent detection from south of Brazil and Uruguay. It was detected in this amateur observatory, UdelaR, in the north of Porto Alegre, in Taquara. You can see here. It was also observed in some surveillance camera. This is in fact pointed to a high school in Castillos, and this is another fireball, another surveillance camera in a farmer north of Castillo, and this is our detection in San Carlos, in the High School Observatory of San Carlos. And you can see here that it was seen in a region that covers over 700 kilometers. So these kind of events could be seen in a very wide place. Okay, so
2 minutes,
this is the end
Gonzalo.
of my talk. No, this is the end of my talk, so I have time for several questions. If you want.
Thank you very much. I'm so sorry for interrupt you in the end. Well, I will stop your sharing. And we have one more talk, and I must apologize Newton Figueiredo is here, sorry, make a host. You have now with all the permissions, Newton. Which is your presentation? Is the presentation under the name of Jamili de Paula? Newton? Are you there? Hello?
Can you hear me? Can you hear me?
Newton, yes, more or less, not so well.
What about now? Can you hear
yes,
me?
now better, yes, perfect.
Oh, okay, I cannot, I just got the video. All right, okay.
No, well, let me know one thing, because my list is, the first author is Jamili de Paula, is right?
Yes, she's my student.
Okay.
I'm the third author.
Okay, well, okay, don't worry. Permit me to present the contribution. The title is A Dialogue Between Vygotsky Learning Theory and Peer Instruction in Astronomy Classes. Well, I think you have also a video.
No, it's a PowerPoint presentation.
No, it's okay, perfect. Well, when you are ready, Newton is from the Universidade Federal de Itajubá, Brazil. So welcome, and your time.
Okay. Can you see the PowerPoint presentation?
Yes, I can. We can.
Right.
So put it in presentation mode.
Is
Yes,
that okay now?
Yes, perfect. Go ahead.
All right, so thank you very much. I'm going to present the talk, a dialogue between Vygotsky's learning theory and peer instruction in astronomy classes. We are three authors. I'm the third author, Newton Figueiredo. We are at the Active Learning Laboratory and the Master's Program in Science Education in Itajubá, Brazil. So peer instruction, as is well known, is a student-centered active learning methodology that was developed by Eric Mazur at Harvard University in the early 1990s. And since then, it has been used throughout the world, especially in STEAM education. So we can summarize peer instruction in this flowchart, and I'll go briefly through it. So usually there is a pre-class task the students do at home. Then in class, the instructor begins with a brief explanation. Then he or she asks a conceptual question. And here's an example of this kind of question. It's usually a multiple choice question with 4 or 5 alternatives. No calculations involved. The idea is to evaluate a concept. Then the students answer the question either using paper and pencil or flashcards, clickers, smartphones, tablets, personal computers, whatever. And then the instructor checks the overall score of the correct answers. And then there are three options. First option on the left-hand side of the flowchart is when a very small number of students get the correct answer, say less than 30%. So what the instructor should do is to go back, explain it again, and go all the way through, ask another question, and then check for the answer. And hopefully, the students will increase their score. Second option is when a large number of students get the correct answer. So when this happens, the instructor goes to a brief discussion and proceeds to the next topic. But what's most interesting is when the number of students who got the correct answer is something between, say, 30 and 70%. Then they interact with their peers. So the instructor asks them to find a peer who chose a different alternative. And one tries to convince the other that his or her alternative is the correct one. So that's why peer instruction. So each topic in a class follows this flow chart, and then the instructor proceeds to the next topic. Our astronomy course, in which we used peer instruction, was an astrometry and celestial mechanics at an introductory level. It was offered along 16 weeks in the second semester of 2018. And the students were majors in meteorology, physics, and chemistry. And many of them were pre-service teacher training students. So each week, the students had a pre-class session on a virtual learning environment, which was followed by two 110-minute long sessions on campus. During on-campus sessions, the students had hands-on activities, problem-solving group tasks, and peer instruction classes. And what's more important, no traditional lectures were given. So here's a few results. This plot shows on the vertical axis the overall score of the class in the second poll. So after the students talk to each other. The horizontal axis is the overall score of the class in the first poll. So this diagonal line shows the scores for which in the first vote and the second vote, they got the same percentage. So there was no gain. Everything above this dotted line means an increase from the first poll to the second poll. And anything below means a decrease. So here are actual results from our class. These two ones shown in red, there was no increase. I mean, the overall score of the class was the same before talking to the peers and after talking to the peers. This one shown in red, actually the score decreases. The score after talking to peers was worse than the score before talking to peers. For all of the other questions, there was an increase. So that means that after talking to their peers, the students learned more than before talking to their peers. And that reminds us of Vygotsky's concept of zone of proximal development. So some students needed the help of their peers in order to learn that given concept that was evaluated in that question. And here I bring a statement of one of the students after the class, in which the student wrote, "This methodology, which requires us to answer the questions and then have a discussion with our peers, was essential for a better learning of the subject. When we talk to our colleagues, those who explain and those who listen to the explanation reach a better conclusion." So that reminds us of two key concepts in Vygotsky's learning theory. First is the use of language while interacting with peers. And the second is the social interaction among students. So, peer instruction and some key elements of Vygotsky's learning theory we can infer from these two examples are the concept of zone of proximal development, the social interaction among students, and the use of language while interacting with peers.
2 minutes. Oh, well.
Thank you very much. And I'll be glad to answer any questions in the question and answer session. Thank you.
Thank you. Thank you, Newton. Very, very interesting job, really. And well, it's time for questions. Give me a moment because I will put my clock to be sure that, okay. Okay, well, there are some questions, and please put the questions. Here is a comment, Gonzalo, by John Briggs. Hello, John. You can read it at a Q&A section at the bottom of the webinar, of the screen. He comments that Chris Peterson of Cloud-Based Observatory in Colorado operates a similar bolide network involving local schools. The software used is based on the METREC from Germany. Very interesting project and excellent for how they involve students. This to you, Gonzalo, if you want to have a feedback.
Yeah, I'm aware of this. There are a few networks like this. One is this, the one that you mentioned. In our case, what we prefer is to develop our own system and also our own software in order to have a better control on the software, in order to make improvements and that kind of things. So, and also it's a good experience for the students to develop the software. So I know that, for example, some networks use this METREC, but this is a closed software. I mean, it's not an open one, and you cannot tweak. I mean, you cannot adjust it.
Thank you, Gonzalo. Emmanuel, you have some comments and questions. There is a question by Cynthia, I think. She's asking about if you have the publications in English.
Actually, I send the mail. I send the link to the chat. There is one publication about SalsaJ in English by Rosa Duran. Actually quite a bit old, but it's still relevant. And my own publications right now are more about in action, about the human orrery. For that, if you want, I can put my website, and there is all references. That's my main subject of research right now. Otherwise, I intend normally to publish in the proceedings of this symposium, and then I will again describe SalsaJ in more details. I guess that's the best way to do.
Okay. Remember, we will save the chat, so we organize all the questions and answers if you write the answer at the website, and we will share everything with the participants. So I am not now all the questions. There are a lot, but there is a question about the well, more or less is all about the language, Emmanuel. The people wants to use the resources, and well, the idea is to use with the students.
I remember there was something in the chat this morning or sometimes about the new astronomical education
Okay.
astronomy education journal. Is that right? The journal launched by the IAU. So I guess in the next publication will be in this journal, so in English. I don't know if it answers.
Nicolas is a member of the local organizing committee. Can you help me with the question for Newton, please? Because I cannot found it.
Hello, everybody. Yes, the question for Newton is from Rade Marjanovic and say, hello from Novi Sad, Serbia. The question for Newton is, in your opinion, is it possible to use the peer instruction method in senior years of elementary school, in particular in classes of physics, with a dash of astronomy, since I'm an astronomer? And best regards, says Rade. I know that, Newton, you just have answered that question, but if you can do it alive, it would be very nice.
Yes, of course.
Thank you for the question. Definitely, yes. I have some students who teach at elementary and high school, and that use peer instruction in elementary school and high school using astronomy, and they do it very successful. So the answer is yes.
Okay. Well, I don't know. I am asking my collaborators if there is any other question, because I am a little lost in the chat. But the most important, yes. Sorry.
No, I didn't see any questions when I read the chat and the question and answers.
Okay.
Those questions were about the references or.
Yes, I know. Well, Gonzalo, there is a group in Brazil who send your greetings, I think. The group is Bramon, and is working. Well, they share a link. They're working in something similar, I think. I believe. I didn't revise the link. So, well,
yeah, I know also that group, and in fact, this video that I show at the end of the presentation from the Observatorio Jungeler, it's from their network. So it would be possible to collaborate.
Well, that is the important thing in this kind of meetings, symposium, congresses, the possibility to contact different people and to, well, think about collaborations. There are a lot of people all over the world making not the same thing, but things which can be part of a cooperation. So it's important to know each other. So we are very, very happy because all of you are here. Okay, well, we are almost at the end of the session of questions. Remember to put the answers at the Q&A section. Revise the time and your name to answer the questions if I forget.